Going back to our trig identities, and we've seen a few now, but another advantage of modarg form is we can bring trig into it, and we can use complex numbers now to create trig identities. So there's very much an interaction between trig and complex numbers. Let's start with one of the first ones we saw. We have a formula for this already, of course, cos 2 theta and sin 2 theta, and I want them in terms of cos theta and sin theta. And we saw a way of creating those. Well, let's create them using complex numbers. See, now we know de Moivre's theorem. I could say cos 2 theta plus I sin 2 theta. Well, that is simply cos theta plus I sin theta squared. So like using de Moivre's theorem in reverse. And I could expand the right-hand side out. Cos squared plus 2i sin theta cos theta minus sin squared. And then we know that the real part must equal the real part and the imaginary part must equal the imaginary part. So if that's the case, cos 2 theta must be cos squared minus sin squared. There's the relationship we know. And sin 2 theta must be 2 sin theta cos theta. Bingo, we got them. Which is a little bit quicker than how we did it before. But by using complex numbers, we've got a nice way of finding these. So all right, let's take it a step further now, because if we had to find a relationship for sine 3 theta and cos 3 theta and tan 3 theta, we would have been applying those sum and difference formulas a couple of times and double angles, and eventually we would get there. But let's use the same idea. Cos 3 theta plus I sin 3 theta would be cos theta plus I sin theta cubed. So I'll expand that out. Cos cubed plus 3i sin theta cos squared minus 3 sin squared cos minus I sin cubed equate the real and imaginary. And there we go. We got a relationship for sine 3 theta. It's a mixture of cos and sines, but we can fix that up, because I can change that cos squared into 1 minus sine squared, and we get a relationship there. 3 sine theta minus 4 sine cubed. And then I can look at the real part, and similarly, that's in terms of sine and cos. This time I'll change the sine squared to 1 minus cos squared, and I get a nice relationship for cos 3 theta. Well, how do I get the tan 3 theta? Well, that's where we remember tan, that's sine on cos. I'll just substitute in the ones I just worked out. But notice, I substituted in the very first one we got, not where we ended up with. Because by doing it this way, it's going to be easier. Because now, if I want it in terms of tan theta, I just divide everything by cos, whatever the highest power is. In this case, it's 3. So if I divide everything by cos cubed, what ends up happening, I end up with all these sine on cos, sine on cos, sine on cos. Oh, well, this one's cos on cos, but that's all right, that cancels. And I end up with, because every one of those sine on cos is tan, 3 tan minus tan cubed on 1 minus 3 tan squared theta. We now have a relationship for tan 3 theta. So I suppose the only time-consuming part of this is how big the power is going to be, because you've got to expand out that particular one so you can equate the real and imaginary. And then the next time-consuming part is, well, if you want it in terms of just one trig ratio, you're going to have to do a bit of substitution of 1 minus sine squared for cos squared and things like that. But now we can do some really interesting stuff. We're going to show that cos pi on 9 is a solution to this equation. Now, cos pi on 9 is not one of our exact values. And normally when you do a show that question, you say, oh, well, I'll just substitute it in and show that it works. But in order to do that, I'd need to know what cos pi on 9 is. Now, that's a bit tricky. I mean, we could play with our alpha plus beta formulas and come up with an answer, but it's not a nice neat one, pi on 9. What's that? Is it 36 degrees pi on 9? Something like that. Now, if we spot something we just saw, that sounds weird. 8x cubed minus 6x minus 1, we actually have the trig identity that we just did. It's hidden in there, but if you look at our trig identities and have a look at the numbers, and it's the cos one I'm interested in here, notice it goes 4 times something cubed minus 3 times that thing. So if I go back here, that's what I've got. Yes, I have to rewrite it. I've got 2 lots of 4x cubed, 4 times something cubed, minus 3 times that thing. It's the same relationship. So if I just simply let x equal cos theta, I can turn this into a trig equation. But the beautiful thing about this trig equation is I now know that this little relationship is cos 3 theta. It becomes a very easy trig equation. Cos 3 theta is a half. Well, and that is one of our exact values. So 3 theta will be, well, in the first quadrant it would be pi on 3. Next time cos is positive is in the fourth quadrant. That's 5 pi on 3. But I need 3 answers because it's a cubic. So we keep going around the circle. Where is the next one? The next one would be at 7 pi on 3. Divide everything by 3, and there it is. There's the pi on 9 we were looking for. Yes, we found the other 2 as well, but pi on 9, that's the number we were looking for. Theta being pi on 9 is a solution to this. Now, 3 consecutive, notice I've bolded unique there, because some will give the same answers. Now, unless there's a double root, if there's a double root, okay, we're expecting 2 that would give us the same answers. But if there's not a double root, then we would skip that and go to the next consecutive one. We just need 3 consecutive unique solutions for this one, because there are no double roots in this. But that's what theta is. The original question was, what is x? We defined x to be cos theta, so we know x is pi on 9, cos 5 pi on 9, and cos 7 pi on 9. They're the 3 solutions to this equation. Well, yes, I've done what they want, and I've done a little bit more, but yeah, x equals cos pi on 9 is a solution to this equation. It now allows us to do things like this. What would this be? Cos pi on 9 times cos 2 pi on 9 times cos 5 pi on 9. Well, hang on. We just found that the 3 solutions, or the 3 roots of this polynomial, are these 3 cosine results. Let's get to this. Well, where were we at? Oh yes, so we know these are the 3 solutions. But we can look at this and go product of the roots, because see how we're trying to go cos times cos times cos. Product of the roots for this one will be 1 on 8. Not quite what they're asking for. Very, very close. Cos pi on 9, cos 5 pi on 9, cos 7 pi on 9. Cos 7 pi on 9, let's think about 7 pi on 9. Where is it? It's in the second quadrant. So the cosine is negative. Its equivalent acute angle would be 2 pi on 9. So I can change that cos 7 pi on 9 into negative cos 2 pi on 9. And I got my answer. So therefore, cos pi on 9, cos 2 pi on 9, cos 5 pi on 9 must be negative 1/8. We're going to create a really nice result, which you can quote, by the way, unless, of course, in the question they've asked you to prove it or show it or something like that. But if they don't, you can quote these results that we're about to create. Z to the power of n plus 1 on z to the power of n, and z to the power of n minus. So basically a complex number and its reciprocal. What do they add up to be, and what's the difference between them? That's what we're essentially finding here. All right, again, via de Marve's, we know z to the power of n is that result, which means its reciprocal, that's like saying to the power of negative n, would be cos negative n theta plus I sine negative n theta. I want it in terms of n theta, so I'm now going to play with the properties of odd and even functions. It will become cos n theta minus I sine n theta, which is really nice because it's basically the conjugate. Makes sense, because remember the quick way of finding a reciprocal, the conjugate over the modulus squared. The modulus of this complex number is 1, so it's going to be over 1. I just end up with the conjugate, in this case to the power of n. But how did I get it? Well, I used the fact that cosine's an even function, so the cos of negative x is the same as cos of x, and sine is an odd function. Sine of negative x is the same as negative sine x. And by the way, if you have been asked to show this result or prove this result, make sure you mention how you jumped from this line to this line. Just like any proof, if it's not obvious, and that's not obvious. How did I go from here to here? Not obvious. You go and explain it. This is how I did it. I used the properties of odd and even functions. Right. Whether you actually write cos negative x is equal to cos x, it's enough to say, well, yeah, cos is an even function, sine is an odd function, so I can make this claim. If I add those two things together, then the conjugates will disappear, and I'll get twice cos n theta. If I find the difference, now it's the real parts that are disappearing, and I'll get 2i sine n theta. As I say, you can quote those unless you've been asked to show or prove them. What does this allow us to do? I can now rewrite something like cos cubed in terms of cos and multiples of theta, just different multiples of theta. Because what I do is I'll replace cos with, well, 2 cos. So I'm going to get a multiple of what I want. But I know 2 cos theta will be z plus 1 on z. Using this idea, n in this case is 1. So z plus 1 on z would be 2 cos theta. I know that to be true. Now I just expand out z plus 1 on z cubed. But because of the symmetry of Pascal's triangle, plus the fact that we're using reciprocals as well, you get lovely patterns where if you group the coefficients that are the same together, that pattern appears. So I've got z cubed plus 1 on z cubed, and then I've also got 3 lots of z plus 1 on z, number plus its reciprocal, which now I can go and use that same formula but in reverse. So the z cubed plus 1 on z cubed I can turn back into 2 cos 3 theta. And the z plus 1 on z, again I'll go back to 2 cos theta. So I've ended up with 2 cos 3 theta plus 6 cos theta. But remember, that was 2 cubed as well on the left hand side. So that's 8 lots of it. Now be very careful when you substitute back in, because it's so easy to cube the 2 in that first one. Because you see z cubed. No. It's always just 2. It's the angle that's changing by that number. So I get 2 cos 3 theta plus 6 cos theta, divide everything by 8, and I have a result. There's an expression for cos cubed in terms of multiple thetas. Ooh, and there we go. Okay, playtime.